So Leslie matrices, they're used to construct models of population growth. So we're trying to work out what's happening with the population over time. So we need to do two things with that one. We need to look at the birth rate. The birth rate's always put on the top of the first row of the matrix, and the survival rate, which is put now after it. That's why you can see the S1 there and so on. Okay, so I'll show you how to put all this together. From there, we might want to do a life cycle transition diagram, which is what this is. These ones here are the survivals, going from one to the other, and then these in red are the actual birth rates for each section, so each age group. So we might have an age group from 0 to 20, 21 to 40, 41 to 60, that's all 20s, and so on. We still use recursion on this. Before we were using, S of n plus 1 equals t to the power of n times s of 0, but now we've got L for the Leslie matrix. And of course, if we want to find the next one, we always get our L, which is like our transition matrix, instead it's a Leslie matrix, and we times it by the initial state matrix of S of 0 or the one before it, if we want a particular one. So if we want S of 16, we'll be doing L times S of 15 if we know F of 15, or if we want F of 15, we'll be putting S of 16 in and so on. But if we just want to find it, we can use it like that. So let's go. Example 1 says use a Leslie matrix and the initial state matrix below to answer the following questions. Okay, write down the birth rate for the age group. So the birth rate, if you remember in the Leslie matrix, it had B1, B2, etc. So there's our birth rates. So the birth rate here, but this one's for age group 2. There's age group 1. Age group 2 is right there. So it's this one here, 1.8. And for the survival rate for age group 3. So the survival rate is after the first line. Age group 3 is right there. So we're looking at 0.3. Is that survival rate? So I'm just going to get rid of all this. Okay, and it says in part B, complete a life cycle diagram. So there are 4 ages, 1, 2, doesn't matter the space between them, try and keep it consistent. Here we've got the survival rate, so this is 0.2, the next one is 0.4, and the next one is 0.3. I'll change my colour. Now we're going to do from here to here, then here to here, and then here to here. This is the birth rate. So 1 to 2 is 1.8. Doesn't matter if you write it above or below the line. 2.6 to this one here, and 0.1 to that one there. So that's our life cycle diagram. Then it says evaluate the following population state matrices, S1, S5, and S20. Well, we know how to do this. The state matrix, S1, we're just going to do L times S of 0. I'm going to do that on my calculator. I'm not going to show you all the steps, but really when I do that on the calculator, you already know how to do this. I'm going to get these answers. That is at 0 there. I better make that a little bit better. S of 5, I'm going to do L of 5 times S of 0, and I will get these answers. 149.76, 26.4, 16.64, and 8.64 matrix. Bracket is a little bit small, and S of 20, I'll make this a little bit bigger, will be, of course, L of 20 times S of 0. So S of 20 is L of 20 times S of 0, and we're going to get 3.84, 0.97, 0.49, and 0.19. Okay, that one was too big. Part D says, given that S of 16, determine S of 17. Well, we're going to use that other rule, S of n plus 1 equals the L times F as S of n, because we want S of 17, which means we've got n equal to 16. So that's how we're going to work that out. Again, I'm just going to do that on my calculator, which I've already worked out, and I end up getting 7.54, 1.91, 0.97, and 0.37. Right, example 2 says, information about a population of female goats is given by the following table. Write down the initial population matrix S of 0. We can see there's the initial population. Of course, when we write it, we're going to write it like this. So 10 in a column, 25, 40, 20 and 15. Then it says use the information in the table, write down the Leslie matrix to describe the change in the population of female goats. So alpha Leslie. Okay, now remember the first one is the birth rates, and there they are, birth rates. So I've got 0, 0.2, 0.9, 0 and 0. Then from the second line is the survival rates, and this 0.6 belongs to the first one, so 0.6, all the rest are 0. The 0.7 belongs to the second one, so 0 there, 0.7 here, because that's the second one. The third one is 0.5, so 0, 0, 0.5. The fourth one is 0.2, 0.2 and 0. I'm sort of squashed them in, and there's no point doing the last one. So there's our Leslie diagram. That'll put these zeros a little bit more to the other side. So 0, 0 and 0. Try and keep them consistently underneath each other, please. Then it says construct the life cycle transition diagram for this Leslie matrix. Okay, so I'm quickly going to do this. I'll do it in blue first. 1, 2. I'll put this one in. This is 0.6. The next one is 0.7 to get to number 3. To get to number 4, it is 0.5. And to get to number 5, it is 0.2. And remember the birth rates up the top. So this one here, you never start off with that one. It's always the second one, so it's 0.2, because that one's going from 1 to 1. Then 0.9, then 0, and then 0 to give myself enough room there. Part D says determine the number of 3 to 4 year old goats in the population after 3 years. Okay, so we're going to work out S of 3, and we're going to do that by doing T of 3 times S of 0. And when we work that out, we get this 8.7, 10.17, 17.22, 2.1, and 1.75. Now remember, if you go back to the table, which I will at the moment, there's the age groups. So 3 to 4 is the fourth number, okay? The fourth number, so because that's 0 to 1, 1 to 2, 2 to 3, 3 to 4, so there are 2.1, so that means it's about 2 goats. So after 3 years, there is 2 female goats. Well, there are 2 female goats, it doesn't matter. We also might want to do the long-term or limiting behaviour population numbers. Okay, example 3 says consider the Leslie matrix L and the initial population matrix S of 0. That should be S of 0. I'll fix it up. There they are. There. Find S of 5. Again, S of 5. I'm just going to write the answers. S of 5 on this one is 1,000. 250, you should already know how to work this out now, and 625. This one here, S of 10, is 2,500. 5, 3, 1.75, and the last one is 218.75, and then S of 50 is 2,777. 063, 582, better write smaller, 688.05, and 244, 521.18. Then it says pre-multiply, so it means multiplying before these matrices by this matrix here to calculate the proportion at each of these stages and comment. Okay, so I'm going to do the first one, which is going to be my 1, 1, 1 times my S of 5. And when I do that, I end up getting 1312.5. So after 5 years, because that's what we're working out. After 5 years, the population is approximately 1312. Okay, so let me do the next one. 1, 1, 1, and the other one I did was S of 10. And when I work that one out, I get 3250. So after 10 years, the population is 3250. We should write approximately, and I'm going to do the last one times S of the 50. And when I work that out, I'm going to get 3604,272.2. So after 50 years, the population is approximately 3604,272. Then it says, and so what seems to be happening, it seems that the population is growing, therefore population increasing. And it doesn't seem to be an end. Part B says determine S of 25 and S of 26. So let's do that first. So S of 25. When I do that, I'm going to get 34781.25. 7297.85, 3062, and S of 26 gives me 41444144.41, 8695.31, and 3648.93. Okay, so I've done up to there. Then it says divide each age group population for F26 by its corresponding grade for S of 25. So that means I'm going to divide this one by this. So I'm going to do that one, and this is to get the rate of increase. So the rate of increase at each age group. Okay, so I'm going to do 4141.41 divided by 3478.1.25, and that gives me approximately 1.1915. If I do the next one, 8695.31 divided by 7297.85 is going to give me approximately 1.1915. And if I do the last one, 3648.93 divided by 3062.50 is going to be approximately 1.1915. So they're all the same. So now I'll be writing that. It suggests that the age group proportion has stabilized after 5 years. Suggests age group proportions stabilized after 25 years, and that in the long run, and that long-term growth rate, as we found it now, is approximately 1.19, or if you want it as a percentage, 19%. Remember the original one, which is the 100%. So that's that part there. Now, limiting behaviour of Leslie matrices. Okay, so over the time, we might find that the age group does not change from one time to the next. Now, this means we can find this real number, K, that this will actually be working for. And this is going to be shown in example 5. In the next example. But example 5, we'll see that sometimes it doesn't work. Example 4 says, consider the following Leslie matrices. Determine S of 10. Again, I am just going to write the answers here. 9906.78. I need to give myself a bit of room here. 4953.39 and 1238.35. This one here is a 14, 20, 542.70, 10271.35, and 2567.84, and the S of 15, 24,651.24, 123, 25.62, and then 30, 81.40, 43. Part B, the rate of increase of the population is constant at each of the age group populations increasing the same way. Find this rate by comparing S of 14 and S of 15. So we're going to do it for each one, but I suppose because it tells us it's constant, we don't have to do it for each one. So I'm going to do the first one, S of 15 and S of 14. So the first one, 24,651.24. That came from there, S of 15. Divided by the S of 14, 2542.70. That equals 1.2, which is the same as the next one, 123 to 25.62, which is the second number, divided by 10271.35, which equals 1.2 as well, and which also equals this one, 4043 divided by 2567.84. They all equal 1.2. Then it says confirm the ratio of the age group population stays constant for S of 0, S of 1, and S of 10 at 841. So I'm just going to put the 841 here. 4 and 1. S of 0 is what I'm going to write now. Now S of 0 is all the way at the top, which is 1600, 800, and 200. And yes, that is in the ratio of 841. S of 1, we got 1920, 960, and we got 240, which is also in the ratio of 841. And S of 10 is 9906.78 to 4953.39 to 1238.35, and they all in the ratio 841. Example 5. Consider the following Leslie matrix with S of 0. Investigate the long-term behaviour of the population if. Okay, let's do part A. B3 equals 8. So we're going to put 8 in there, and we're going to work out S of 1. When we work out S of 1, we get 0, 250, and 0. We're going to work out S of 2, and when we do S of 2, we're going to get 0, 0, 125, and S of 3 equals 1,000, 0, and 0. And you'll find that if you do S of 4, it goes back to S of 1. So this one repeats, okay? Repeats the 3 steps, or states, I should say, above. Okay, now we're going to put B3 equal to 4. Now, because it's 4, I'm going to do different. I'm going to still do S of 1. I still get the same answer, 0, 250, and 0. I'm going to go S of 5 now, because it's not a 3 anymore, and we have 3 here, so that's stated to it. It's a cycle of alpha cubed, which is the same as I. That's why that happened for the first one. So I'm going to do S of 5 here, and I'm going to get 0, 0, 62.5, and I'm going to do S of 50 to see what's happening, and I get 0, 0, and 0.0019. So what's happening? It's decreasing. So this is population decreases over time. And now we'll do it when B3 equals to 10. So S of 1, I still get the same thing, 0, 250, and 0. I'm going to do S of 5 again. S of 5 gives me 0,156.25, and I'm going to do S of 50, which gives me 0,0 and 440.89. So this is increasing. So the population increases over the long term.